Okay, let's get started. Good evening, everyone. Welcome back. For those of you guys on Zoom, can you hear me and see my share screen? I need to ask the same question before each class. Okay, thank you. For today's class, will be the first class of the cycle of week 2. Probably you have noticed that there are 3 sets of lecture notes for this cycle for week 02. The first set is about Cartesian coordinate systems and the lines. So I'm not going to go over this set of lecture notes in class. So you guys can review by yourself, and if you want, you can complete the corresponding quiz and homework. So in today's class, we're going to cover lecture 04 on Canvas. Okay. So the main topic today will be functions. So we are in the summer, and obviously, I think we sometimes enjoy some cold juice in the summer. So I want to make an analogy between a juice machine and a mathematical function here. Okay, so what you can see in this picture here is my juice machine. Okay, so this is the machine. So this machine takes fruits as the input and makes juice as the output, or say as the product. And so as you can see, right, I sketched this machine such that this whole diagram looks like y equals f of x. So a mathematical function is kind of similar to a Jewish machine. It takes a number as the input and then makes a number as the output, as the product, okay? And so here is the definition of a mathematical function. So a mathematical function is a number machine. And this number machine maps, okay, each element from a collection, from a set, say set D, to an element, say Y, in another set. So if I read this definition here, right, a function f from a set D to a set E is a correspondence, or say a mapping, that assigns to each element x of D one element y of E. Okay, I think we should be all familiar with this concept because we learned functions in algebra 1 and algebra 2, right? So sometimes we can denote this correspondence in this manner. D, we put an arrow and put F on top, and then to E, right? So F is my machine, right? So this F maps, we'll say, okay, maps each element in this collection, in this D, to an element in this collection, in this set E. So that's one notation for a mathematical function. Or sometimes you can see this notation here, F colon D right arrow to E. I think this notation somehow tells us what a function does, right? So this F is the name of this machine. So this machine, okay, produces an output using each input. Okay, each input is from this collection of D, and each output is in the collection of E. Okay, so that's why we have this D right arrow to E. So it's a mapping from D to E. Okay, sometimes you see this graphic representation of a function, right? So we use a circle or sometimes use other shapes, right, to denote a collection of inputs, and the E action of outputs, and then you draw this arrow here, okay? So I think we are all familiar with this mathematical notation, y equals f of x, right? Y equals f of x. So f is the name of this function, right? Is the name of it, just like in the previous analogy, right? So we have a name for this machine, right? We call it a Jewish machine, right? A Jewish machine is the name of this machine. Okay, so fruits are the inputs for this machine, and the juices are the outputs of this machine. And similarly, a function is a number machine, and in this case, we name this machine F. And you can name it G, you can name it H, you can use other symbols if you want, okay? And so we put this name here, then we have round parentheses, right? X represents the input to this machine, okay? So this machine, right? I draw this diagram here, right? So this machine F takes an input, say X, then makes an output, say Y, from letter X. So how letter Y is made from letter X? So we have Y is made as a F of letter X, right? So F works on that X, okay, to make Y. Okay, so that's kind of very natural notation for this, okay? I forgot who initially introduced this notation for functions, probably Euler. Okay, how this machine makes Y from X, right? Makes the output from the input. So, of course, different machines have different mechanisms. Okay, so different functions can have different rules. We say rules. Okay. So F tells us how to make a Y from X. Sometimes we are given the rule for this machine. So we write down F of X equals X squared minus X, for example. So that means the rule now is X squared minus X. So you give me an X as input. So this machine then square the X and subtract the result and spits out the output as X squared minus X. Okay. So if F of X equals X squared minus X, meaning the rule of this function to make the output is X squared minus X, is this mathematical expression in terms of X. Then the output Y is X squared minus X, right, for each X. So so of course, in this case, X is just a variable that represents the input. So if X equals 1, in this example here, then what's the output? So output Y is F of that 1, right? So F works on that 1, on that number 1 as the input. So then you say, oh, how to make that output according to the rule? X as the input, output is X squared minus X. So if 1 is the input, then it's 1 squared minus 1, right? So then you say Y squared minus 1 equals 0. You get the output as 0. And if X equals 2, and similarly, then Y is F of 2, which is 2 squared minus 2. You get a 2. Okay. So when you plug in a value for X and evaluate that rule, this is called the evaluation of a function. Okay. So two very important concepts are associated with F. One is called the domain of this function. The other is called the range of this function. Okay, so when you write down this notation for the function f, y equals f of x. So this x is called an independent variable that represents the input, right? And y then is called a dependent variable that represents the corresponding output. And probably you can comprehend why x is called independent and y is called dependent. Can you make sense of that? Because you provide x to that machine, then y is not dependent, is not independent anymore. Y must be computed using that x. So y depends on that x, right? The output depends on input. So that's why x is free. X can take whatever value from the domain, from the collection. But y, for any input, then y is determined by that x. So y depends on that x. So y is called a dependent variable, and x is called an independent variable. So the set D, or say the collection, or say the family, right, of numbers, or a collection of numbers. So set of D from which independent variable x takes its values is called the domain. Okay, so domain is just basically it's just a storage of the raw material for your machine. Okay? And the range R is the set R that contains all possible values of y corresponding to all the x values in the domain. So basically, range R is like a storage of what? Of the products from the machine, right? From the machine. So if you consider that analogy, right? So maybe in your home kitchen, you have a basket, right? To store different kinds of fruits, apples, bananas. So that basket, that collection of fruits is the domain of your juice machine. And then, of course, you can use all these fruits to make different kinds of juices, right? In your refrigerator, and you have a collection for different kind of juices. And that's the range of your juice machine, okay? So now, okay, so in another shell, right? So you see, we have a machine, a number machine called F. And this machine assigns each value in the domain, right? Say X in the domain, a value in the range, right? A value in the range. Okay, so X. So this symbol here means is in, right? Are you familiar with that? So this symbol means is in. So X is in D. So F assigns X a corresponding value of Y, and that Y is made from X as F of X, right? So in many situations, you know what that F of X does, right? So you have an expression in terms of X, okay? So Y is in the range, right? Y is in the range. If the domain of a function is not specified to you, then normally we find the so-called implied domain. So the implied domain of a function is just all possible X values for which this F of X works well. Okay, F of X is defined. Right. So suppose you have a juice machine. I don't give you a manual, say, this is a juice machine. So what's the domain for this machine? And you say you say it's a collection of what? Of different kinds of fruits, right? So you don't want to use stones, use other nasty stuff as the input to this machine, right? So implied domain, okay? So for example, suppose I give you this function f of x equals 1 over x. So what's the domain of this function? If I don't specify the domain, then you find the implied domain. And you know this machine is happy, or so this number machine is happy if the input is not 0, right? So 1 over x, you can divide 1 by any non-zero number. So x can be any real number except 0. So what's the implied domain of this machine, of this function? X is not equal to 0. And you can write down this domain in terms of the set notation. This is the so-called set notation. So D represents the collection of inputs, okay? So D equals, so we use curly brackets to denote a set. But then we say, oh, this set is all the values of X, right? So X, under the condition what? So we have X, we put a vertical bar. So then this vertical bar means under the condition, X is in what? In R. So this black bold letter R represents set of all real numbers. Okay. So I introduce some notations later on, so you guys are comfortable with those mathematical notations. Okay. So of course, also we require X be non-zero, right? X be non-zero. So this is a way, another way to write down the domain of this function. Okay. Of course, you can use your words. You say, oh, the domain of this function is all the real numbers except 0. But sometimes we don't write down all these words, right? So you can mathematically just write down x is not equal to 0. X is in the set of real numbers, right? You can write down domain in this manner. Now, if I challenge you, so we know the domain of this function is all the real numbers except 0. So keep in mind, in PreCalculus, okay, so we consider only real functions, okay, functions that take real numbers as inputs and spit out real numbers as outputs, okay? So consider this real function f of x equals 1 over x. And we know the domain of this function is the collection of all real numbers except 0. So can you tell me what's the range of this function? So what's the set of all possible outputs from this function? So what's the range? The range is all the real numbers except 0. Okay, right? Why? Because y is equal to 1 over x. So that means you can rearrange this equation to write down x as 1 over y, right? So x and y, they are mutually reciprocals. Do you agree? So you know x is equal to 1 over y, and we know x can be any real number except 0, right? So when you look at this expression here, you see x equals 1 over y. That means this y can be any real number to give you like x, right? Except 0. So when you look at this expression here, x equals 1 over y, then somehow you know this y can be any real number. For each real number, you can find the corresponding x as the input to produce that y. Right? For example, if y equals 2, what's x? X is half. Oh, to get 2 as the output, I use half as the input. Clear? And if y is equal half, then x is equal to 2. You say, okay, if I want to get a half as the output, I use 2 as the input. So but this rewritten form of this function tells you this y can be any real number except 0. Because for any real number, you can find a corresponding input to produce that real number. So the range of this function would be all the real numbers except 0. Okay. And in algebra 2, we learned the graph of this function. Do you remember the graph of this function? Y equals 1 over x. This is the simplest rational function, right? 1 over x. Yeah, hyperbola is called a hyperbola. It has 2 branches. One branch in the first quadrant goes like this, as you can imagine, right? So as x getting bigger and bigger, and y is getting smaller and smaller in this first quadrant. And then you have another branch in the third quadrant. Okay, so you as you can clearly see, x can take any value except what? Except 0 here. And also y, as you see, this curve shoots towards infinity to negative infinity. So y can also be any real number except 0 here. Okay. Okay. So when we read the definition of a function, keep in mind, pay attention to this key word here. So this machine or this function f assigns each element in the domain. How many elements in the range? 1. Okay. So for each input, there is only 1 output, not 2, not 3, only 1. Okay. For each input, this function produces 1 output. Okay, 1 output. So for example, so let's consider this function y equals x squared. We have this equation here, y equals x squared. And this equation actually represents y as a function of x. Why? As you can clearly see, when you supply a value for x, you square that value, you get 1 output, right? So for each x value, you get 1 y value. For example, when x equals 1, okay, that's a 1 input, right? How many y values you can get from this expression here, y equals x squared? Then y is 1 squared, just 1, right? If x equals negative 1, again, you can only get 1 output, which is 1, right? Y equals negative 1 squared is 1. But in this case, we have the same output for 2 different inputs. That's okay. Keep in mind, okay? So you see, when x equals 1, you get 1 as the output. When x equals negative 1, you also get 1 as the output. That does not violate the definition of a function. As long as for each input, there's only 1 output. Okay, maybe multiple inputs they lead to the same thing. That's okay. Okay, as long for each of them only leads to 1 number. Okay, 1 number. However, if I give you this expression, x equals y squared, and obviously in this case, x must be non-negative, right? Because x is a real number squared. Okay. So can you regard y as a function for x? So in this case, x represents input, y represents output. Now, if x and y satisfy this relation, x equals y squared, can you regard y as a function of x? And what do you see? For example, if x is 1, okay, I supply 1 as the input. for this relation, I'm not saying it's a function. I don't know if it's a function or not. Okay. Suppose x is equal to 1. Now, how many y values you can get? X equals y squared. So if x equals 1, y can be positive 1, and y can be what? Negative 1. So we cannot regard this relation as a function of x, because for one input 1 for x, you have two outputs for y. One is 1, one is negative 1. Clear? So x equals y squared is not a function of x. Okay, it's not a function of x. So that's a very important point you need to be aware. So let's consider this first pro question here. Okay. Does the equation the absolute value of y equals x define a function y equals f of x? So when we say y equals f of x, that means x represents the input, y represents the output. Okay, y as a function of x. Yes or no? Okay, this is just a yes or no question. Okay, I'll give you 30 seconds. So keep in mind, okay, to be a function, okay, the relation assigns each input only one output. You can try. For example, you let x be 1 and see how many outputs you get. If you can only get one output, then probably it's okay. But if you can get 2 or more, then this relation or this equation does not define a function. So is this a function? Obviously, yes or no? No. No, right? Okay, you guys can be a little bit more active, okay? Okay, so obviously it's no, okay? No, because, right, you have this relation here. X value of y equals x. Now suppose my x is the input, right? We regard y as the output and x as the input. Okay. You can try. Suppose I say x equals 1. Okay, you supply 1 as the input to this relation here. Okay. According to this relation, then what's the absolute y? Absolute y would be equal to x equals to 1, right? Of course, in this case, x must be what? X must be non-negative because x is the f value of y, okay? So absolute y equals 1, so how many y values do you have? So that means y can be 1 or negative 1. So you see, so for each input value, for each non-zero input, you can get a 2 outputs, right? So that means this relation is not a function. Okay, it's not a function. So the answer is no. What does that mean? Graphically, I will show you later. Okay, so when we talk about the graph of the function, so we'll have the so-called vertical line test. Okay, to test if a curve is a function, is the graph of function or not. Now, so if you are given the mechanism of your function, or say you're given a rule, so now if you know the rule, you say you know how this function works, then you can easily find the output from the inputs, right? So that's called a function evaluation. And normally that's quite easy, okay? So let's consider this function f of x equals the absolute of x minus 1. So I don't know if you're confused here, right? In the previous poll is the absolute of y equals x. We know that equation is not a function, does not define a function, okay? But if I have y equals absolute of x, is this a function? Then this is a function of x, right? Because the f value of any number is just a positive value, one positive value. You cannot have different answers, okay? So this is no but this one actually is yes. Okay, this is a function. This is not a function. Okay, so this is the function f of x equals the absolute of x minus 1 is a function of x. So if I ask you to evaluate this function at a 2, then you just supply 2 to this function, right? You replace this input variable x. This x represents the input. Now I know that the input is 2, right? So you replace x by 2. Then you find f of 2 is equal to the f value of 2 minus 1. And you get what? Absolute of 1, which is 1, right? Just one value, right? One value. And how about the f of negative 2? If you plug in negative 2, you have absolute of negative minus 1, which is absolute of negative 3, which is again positive, right? Positive 3, one value. Okay, so this is the evaluation of this function. Okay. However, this function can be written in a piecewise manner. Because if this x minus 1 is non-negative, say 0 or positive, then the f value of this x minus 1 just itself, right? The f value of a positive value is just the positive value itself. The f value of 0 is just 0 itself, right? So then you say, okay, so if x minus 1 is greater than or equal to 0, or say x is greater than or equal to 1, f of x is just what? X minus 1. Remember that? However, if x minus 1, this expression is negative. So, for example, the absolute in this case, for example, the absolute of negative 3 actually becomes what? Becomes positive 3. So, if x minus 1 is negative, or say x is less than 1, then f of x is equal the opposite of this expression, right? So it's a negative of x minus 1, which is 1 minus x. So this function can be written in this piecewise manner. Okay, so when x is greater than or equal to 1, f of x is x minus 1. Because the absolute of x minus 1 is just x minus 1 itself. X minus 1 is positive or 0. However, if x minus 1 is negative, then the absolute of x minus 1 is the opposite of x minus 1. So it's a negative of x minus 1, which is 1 minus x. Okay. So if we are given this piecewise function, now suppose, okay, I have this piecewise function. I ask you to evaluate this function. What is f at 2? When you read this function here, it's if x is greater than or equal to 1, is 2 greater than or equal to 1? Yes. Then you need to use this x minus 1, use this piece to evaluate this function. Clear? So then you say, because 2 is greater than or equal to 1, so f of 2 would be 2 minus 1. If I ask you to evaluate f at negative 2, now you know, negative 2 now is less than 1, right? So then which piece you want to use now? You need to use 1 minus x to evaluate this function, because now my input is less than 1, right? So then you have f of negative 2 is 1 minus negative 2, you get a positive 3, right? Which is, of course, consistent with this evaluation here. Okay? But I hope you know how to easily evaluate a piecewise function. When you have a piecewise function, you have multiple pieces. You need to determine this input falls on which piece, right? You use that piece to do the evaluation. Is that clear? So this is the simple stuff. Okay, so I'm not going to write down my answers on new pages. Okay, so I just quickly go through this stuff. I will slow down when we do more challenging problems. Now, we have a little bit more challenging problems. So keep in mind, f of x normally is given in terms of an expression of x, right? For example, x squared, absolute of x minus 1, or maybe later on you say e to x, the natural log of x, and you have all these kind of expressions in terms of x, right? So that's the rule, right? So if you know the expression in terms of x, that means you know how this function works. Okay, you know how this function works. Okay, but you keep in mind this x in this expression here is just a placeholder. Just x is just a variable that represents an input, right? Represents a number supplied to this machine, right? Just represents a raw material for this machine to work. So as long this x is representing a number, and you can plug in that number. If this number is in the domain, you can plug in this number and apply this rule to find the output. Okay, so letter X as a whole is called a placeholder. So when we say, for example, f of x equals 1 over x minus 1. Oh, I know how this machine works. This machine subtract the inputs by 1, then do the reciprocal. Right? That's how this machine works. So keep in mind, this x is a placeholder. You can replace this x by an empty box. So f of this box then is 1 over that box minus 1. Right? You can replace this x. You have x here. You have x here. So f on that x is 1 over x minus 1. So f on that blank box, if that blank box represents a number, then it's 1 over that blank box minus 1. Also, this empty box minus 1. Why am I saying this? So now, okay, so let me show you some examples. Of course, if I just give this function a number, say 2. So what is f of 2? Very easy. You replace that x by 2, right? You get a 1 over 2 minus 1. You get the output. Now, if I supply 2 plus 1, so what is the f of 2 plus 1? Then this 2 plus 1, at the end of the day, we know it's 3, right? It's a number, right? So it can be used as an input. So what is the f of 2 plus 1? I treat 2 plus 1 as a whole. Okay? Then you replace that x by what? By that 2 plus 1. Because 2 plus 1, you just wrap it up inside that box, right? It's just a number. You just replace that x by that number. So f of 2 plus 1 would be 1 over 2 plus 1. Then minus 1, right? You get 1 half. Now let's go a little bit further. So this time I ask you, what is f of a squared minus a plus 1? So what's the input now to this machine? The input to this machine is a squared minus a plus 1 is this whole expression in terms of a now, right? And keep in mind, this is just an algebraic expression. At the end of the day, this expression represents a what? A number, right? It's a number, right? But this number is written in this form a squared minus a plus 1 now. So then if I want to evaluate f at a squared minus a plus 1, then you just replace that x by what? A squared minus a plus 1. Does it make sense to you? So that x can be replaced by a number, by a numerical expression, say 2 plus 1, can be replaced by what? By an algebraic expression, such that a squared minus a plus 1. So then you do that simplification, 1 and 1 cancelled, you get 1 over a squared minus a. Is that clear? So keep in mind, okay, later on, I ask you to evaluate the function at an expression. You just replace x by that expression. This is very useful for us to understand composite functions later. Okay, composite functions later. So let's do a practice here. F of x is defined in a piecewise manner. F of x equals x squared minus 1 if x is less than 1. F of x is equal to x minus 1 if x is greater than or equal to 1. What is f of a squared plus 1? So now the input to this machine is this expression, a squared plus 1. How are you going to evaluate this function? 30 seconds, okay? Again, this should be straightforward. Okay, 20 more seconds. Okay, which answer choice is the correct one? Jay, what's your answer choice? You agree? B. What's your name?
Jacob.
Jacob, can you explain why the answer should be B?
You know that a squared plus 1 is always greater than 1.
Mm-hmm.
You just plug it into the piecewise, you get a squared.
Okay, good. So, because you guys talk a lot, so I just want to check you guys. Okay, so the answer should be B, okay? So in this case, the input to this function is this expression a squared plus 1. As I said, we consider real expressions, okay? A represents the real number. Then we know a squared is always non-negative, right? A squared is non-negative. So that means a squared plus 1 would be greater than or equal to what? 1 now. You add 1 by something bigger or equal to 0, right? You get something greater than or equal to 1. Okay. So because the input is greater than or equal to 1, now according to this expression here, so what is f at this a squared plus 1? So you need to use which piece here, because the input here is greater than or equal to 1. You need to use this piece. So it's x squared minus 1. So you replace this x is the placeholder, right? So x now is replaced by this input, a squared plus 1. So it's a squared plus 1 and minus 1. So you get a squared, right? Okay. Okay, so so far we considered some basics about the functions. Okay, and functions are extremely important in mathematics. Okay, so functions are extremely important objects. And why we want to study functions? Because a lot of real life relations can be modeled by functions. For example, so if we want to predict the weather, right? For example, you can think that the temperature at a particular location is a function of time and a function of that location, right? So then we have models try to find that function, okay, to predict the temperature, to predict the weather, okay? And this happens in many applications. So let me give you just a very simple example, okay, to appreciate the usefulness of functions. Okay, so for example, in algebra 1, we studied a linear function y equals mx plus b, right? M is equal to the slope, b is equal to y-intercept, and the linear function can be used to model linear growth or linear decay, right? For example, if you consider the conversion of the temperature from Fahrenheit to Celsius, then we have a relation of the temperature in these two units, then that relation is a linear relation, okay? Now, let's consider this example here. Suppose I have a rope with length 1. I want to use this rope to enclose a rectangle, okay? To enclose a rectangle such that one dimension of this rectangle is x. Now I want you to find the area of this rectangle in terms of x. So the area of this rectangle can be written in terms of x as a function of x. Can you build that function? So that's easy, right? So if the length of this rope is 1, so you enclose this rectangle by that rope. That means the perimeter of this rectangle is equal to what? What's the perimeter of this rectangle? Is equal to 1, right? Is the length of that rope. Okay. So if the perimeter is 1, so we know if this dimension is x, then this one is also x because this is a rectangle. Then we know x plus this guy would be 1. So as you can see, this dimension here should be what? 1 minus x minus 2x, and divided by what? Divided by 2, right? Because you have 2 pieces here. Right? So that's the dimension for this guy here. Okay, so then you know the 2 dimensions of this rectangle. So what's the area? The area, suppose I represent the area as y. So y equals x times 1 minus 2x over 2. See? You can use this function to model the area of this rectangle in this case. And later on, I may challenge you, how are you going to determine that x to make this area largest? Right? So you can solve such a real world problems. Okay, real world problems. Suppose I'm a landlord. Okay, I give you this rope here. I say, okay, I have a lot of land. So I'm generous. I give you, I want to give you some land. You use your rope to enclose a rectangular shape. That rectangular shape is yours. Then you need to think about how I'm going to do that rectangular shape to get the largest area, right? So we have this problem here. Clear? So you need to do this model the area of this rectangle as a function of one side x. Then you try to maximize this function and see how to choose the x to make y largest. Okay, we are going to solve this problem in the next class. Okay, now next, let's consider graphs of functions. So keep in mind, a function assigns each x value one y value, right? Y equals f of x assigns each x value one y value. So if you put this x value and the y value together, okay, then you can form an ordered pair of numbers, right? See, x comma y, right? X comma y. So x comma y. So of course you can regard x comma y as the coordinate of a point in the 2D plane, right? So with the x coordinate being x, y coordinate being y. Clear? So now you can see for each input there is one output. So then for each input, one output, you can put it together, you get a point. Then you change the input, you change your x value, you get a new y value, and you get a new point. So if you do so basically, so this function now, okay, graphic speaking, this function graphic speaking generates of what? Points, right? Points. For each input, each output, one output, tail number, 1 point, right? So if you plot all the points generated by this function, then you get the graph of this function. Clear? So the graph of this function basically is the collection of all the points produced by this function, because we know this function generates all the pairs of numbers, right? Input, output, put it together. Input, output, 1 point. Input, output, another point. Input, output, another point, right? So if you put all these points, you get the graph. And normally, right? So you will see. So you get a curve. So it's a collection for points. You get a curve for the graph of this function. Okay, because x can change. If x changes continuously, and y also changes continuously. Okay, so in this diagram here, so we pretend this green curve is the graph of this function y equals f of x. So if I supply a as the input to this function, then I get a b as the output. So what's that b value? B is f of a, right? So the y coordinate here, b, is f of a. It's just evaluate the function at a, you get the output. So a comma b, well, b equals f of a is a point on that green curve. And you can change your input, you get a different curve point on that function. Now I think we can understand that a very key important point about the definition of function. We say a function assigns one output for each input. Meaning what? Meaning what? If you draw a vertical line, that vertical line can intersect the graph of this function at most once. Do you agree? Otherwise, if suppose you have a curve looks like this, and you think, oh, this is a graph of function. You say, oh, let me draw a vertical line here. Now this vertical line intersects this curve twice. That means for this particular input, for example, this is 1. Then you can get a 2. Say this is 2. Suppose this is 3. Then you have 2 outputs, right? 2 or 3, right? So that violates the definition of a function. Clear? So a vertical line can only intersect the graph of a function once, at most once, because we can only have one output corresponding to each input. Okay, so this is the so-called vertical line test. So a curve in the coordinate plane is the graph of function if and only if no vertical line intersects, sorry for my grammar mistake, intersects the curve more than once. Got it? So that's a very easy way to test if you know the graph of a function. So for example, is this curve can this curve be regarded as a graph of a function? Yes, because it passes the vertical line test, right? If you draw a vertical line can intersect this curve at most once. Is this one a function? Yes, right? Even though you may have two different inputs that leads to the same output, that's okay. Okay, that's okay, right? But for each separate input, there's only one output. Okay, one output. Is the circle the graph of a function? No, it fails the vertical line test. And for this case, okay, I want you to remember, sometimes you may see this kind of a bizarre function. Okay, so you see a jump at x equals 1. And so at x equals 1, so obviously to the left 1, right, you see this curve, and it passes the vertical line test. To the right of 1, you see this curve, it passes the vertical line. So I use an open circle on this, at the end of this curve, and a solid circle at the end of this curve. Meaning what? Meaning f at 1 is given the y-coordinate of this point. That open means that point is rooted, okay? So remember that fact, okay? When you see an open circle on a curve, that means that point is excluded. Okay, if that point is included, you need to use what? Solid dot. Okay, solid dot. Okay. Okay. Now let's define some properties of. Okay, to do so, let's first of all familiar with some. If x is less than or equal to a, then we say x is between a and b. Okay, including a and b. Okay, so you can write down. We say, right? So this. Then we have the interval notation, right? This is called a interval. We use a square, okay, to include a and b. X is between a and b, including a and b. And if you draw that interval on the number line, this way, you use solid dots for a, you use solid dots for b. To online folks, sorry, I just lost the connection. So can you guys now hear me and see my screen now? I have not shared my screen yet. Okay, let me share.
Yeah, we see it.
Okay, now it's good. Okay, sorry for that. I think that my internet connection was lost suddenly. I think we lost the connection here, right? When I talked about open intervals. Is that right? Yes. Yeah, open intervals. Okay. So now, okay. So of course, sometimes if we want to, to use an interval to describe the whole real number line, then we say the interval is from -infinity to the positive infinity. Okay, so I hope you are also familiar with these two notations, right? This is line 8, okay, is called infinity, right? -infinity, positive infinity. So if x is any real number, you can say x is in the interval from -infinity to positive infinity. So this interval represents all the real number, right? Or the whole real number line, okay? Now, so we can discuss the increasing and decreasing behavior of a function, okay? So we say a function f is increasing on this interval from a to b. We mean that the graph of this function rises, okay, from a to b, from left to right. Okay, so as x increases, y increases. Okay, so if you supply a bigger input, you get a bigger output, right? So as the input increases, the output increases accordingly. Then we say the function is increasing, right? Very natural definition, okay? Algebraically speaking, we say if x2 is bigger than x1, then f at x2 is bigger than f at x1, okay? And in contrast, we can define the decreasing behavior of a function. So if f is decreasing on an interval from a to b, then we know the graph of this function from left to right falls down, right? Falls down. Okay, so meaning bigger inputs leads to smaller output. Algebraically speaking, you say x2 bigger than x1, right? x2 is the bigger input, right? Then f of x2, that's the output, right? Is smaller than f of x1. Then we say the function is decreasing. So you need to understand these properties both graphically and algebraically. Okay, so later on, sometimes you don't have graphs, you just do this kind of algebraic discussions, okay, to see inequalities. And finally, we say a function is a constant on the interval from a to b, meaning what? Meaning for any input on that interval, the output remains the same. So the graph on that interval now is a horizontal, right? A horizontal line, horizontal. So this is a very lazy function because this function just spits out the same number as the output for whatever inputs, okay? So the graph is a horizontal line, it's a constant function. So now I want to do a more comprehensive example here. So this time I want to do this problem on a separate page. I give you this function. F of x equals the square root of 9 minus x squared. I ask you to find the domain of this function, the range of this function, and the graph of this function. So how to do this problem here? So what is the domain of this function? So in this case, we need to find the implied domain because the problem does not give us the domain, right? So then you just need to find the domain of this function such that this function is happy, okay? Is happy for all the values in the domain. So obviously, f of x is the square root of this expression. So of this quadratic expression. So we require to find the domain, we require what? We require this 9 minus x squared. This expression should be non-negative because this is under the square root, right? We agree? Yeah, that's right. Okay. So then you solve this inequality to find the range for find the values for x. Okay. So of course you end up with 9 greater than or equal to x squared. We'll say x squared is less or equal to 9. So if x squared is less or equal to 9, what you can say about x? So x should be less than or equal to 3, but at the same time, x should be greater than or equal to what? -3, right? So what's the domain of this function? Domain of the function is between -3 to +3, inclusive, right? Inclusive. So domain of this function d is equal. I want to use the interval that is from -3 to +3, inclusive. Okay, you can write down the domain in this manner. Now, how about the range of this function? Can you find the range of this function algebraically? So y is the square root of 9 minus x squared, right? Let me ask you. So this 9 minus x squared, what's the smallest value for 9 minus x squared to make this function happy? Should be what? 0, right? So 9 minus x should be at least 0, clear? 0. But what's the biggest value you can get for 9 minus x squared? Right? This is the requirement, right? To make this function happy, right? So this is required by the square root, right? Square root is happy only when this 9 minus x squared is greater than or equal to 0, clear? So that's the way we find the domain. But can you tell me 9 minus x squared 9 minus x squared is less than or equal to which value? So what's the maximum possible value you can get for 9 minus x squared? So it's less than or equal to what? Keep in mind this x squared, right? X squared is always 0 or positive. So you subtract 9 by something 0 or positive. You make it, if you subtract the positive value, you make it smaller, right? So what's the maximum value you can get? You subtract 9 by what? By 0, then you get the biggest value. As long as you subtract the other positive value, then it's getting smaller, right? 9 minus 1 is 8 now. 9 minus 2 is 7. So 9 minus 0 is the biggest value you can get for 9 minus x squared. So this is less than or equal to 9 minus 0, which is 9. So 9 minus x squared is between 0 and 9. Now, how about the square root of 9 minus x squared? So it's between square root of 9 and the square root of what? And 0, right? So square root of 9 minus x squared. So square root of 9 minus x squared is less or equal to 3, greater than or equal to 0. You take the square root of the range from 0 to 9. Then you get a 0 to 3 now. So what's the range of this function? So range of this function is the interval from 0 to 3 inclusive. Got it? How about the graph of this function? So keep in mind, the output y is computed from the input x as square root of 9 minus x squared. So it's a little bit hard to see what kind of curve you get. Okay, you can try to use a brute force approach and use a bunch of x values in the domain to find the y values. Then you mark all these points, right? That's time consuming. However, if you look more closely, you see y squared is equal to 9 minus x squared. You can square both sides. get rid of the square roots. Then it turns out you have x squared. You move this to this side, you have x squared plus y squared equals 9 squared, which is 3 squared. Do you know what's the graph of this equation here? X squared plus y squared equals 3 squared. Are you guys familiar with that equation? This is the graph of what? Of a circle, right? Of a circle. Did you learn this? So it's a circle, okay? So the graph is a circle. What's the center of this circle? Center is the origin. What's the radius?
Origin.
Yeah, so the radius is 3, right? So you draw that a circle here. Okay, let me draw this circle. Use dashed line first. Do you think the graph of the function is the whole circle? And I think we know, we already told you that circle cannot be the graph of a function. This y equals a positive square root of 9 minus x squared is just the upper branch of this circle. Do you see that? So this is the equation for this whole circle. But my function y is a positive square root of 9 minus x squared. Because when you look at this circle equation can be written as y squared equals 9 minus x squared. And then you know the y can be written as a positive square root of 9 minus x, 9 minus x squared, or y equals a negative square root of 9 minus x squared, right? Because for each 9 minus x squared, it has 2 square roots, positive 1 and negative 1. So there you know this positive portion is this guy, y is non-negative, right? So it's y equals a positive square root of 9 minus x squared. This dashed part, this below part here, is y equals a negative square root of 9 minus x squared. So this circle can be regarded as the graph of 2 functions. The upper one is a positive square root of 9 minus x squared, y is positive, right? And the bottom one is y equals negative square root of 9 minus x squared. Got it? And I think if you look at this graph here, you can see. So what's the domain? From negative 3 to positive 3. What's the range? From 0 to positive 3, right? Because this half a circle as the graph. Does that make sense to you guys? Okay, good. Do you guys need a break? I believe so, right? Okay, let's take a short break, a 5-minute break. Okay, then we introduce more properties. Any questions?
Yeah, it was, bro.
I don't want to say, you know.
Okay, do you guys have enough rest? Well, let's resume the class. Okay, guys. And guys, all time, if you have a lot of time, you Okay, please turn in your cell phones if you cannot control yourself in the class. Okay. Also, after class, please turn in your work on all these poll questions. Okay. So don't forget to write down your full name on your work. Okay. And after class, please turn in your work. Now to those of you on Zoom, okay, you submit your quiz at the end of the class. Okay. Now we are ready to resume the class. So are you guys ready? So are you guys on Zoom ready? If you are, please let me know by raising your hands. Okay. So to focus on Zoom, please come back and raise your hands to let me know you are ready to continue. Don't lower your hands yet until you tell you to do so. Okay, you can lower your hands. So let me continue. So by the way, in the previous example, and we know the graph of this function is the upper portion of the circle, right? And if I ask you on which interval the function is increasing, I think you can easily see from the graph. So on the interval from -3 to 0, right, the curve rises from left to right. So the function is increasing on that interval from -3 to 0, right? And the function is decreasing on the interval from 0 to 3, right? As you can clearly see that. Okay. Now, lastly, I want to introduce odd and even properties of some functions. Okay. So let me start with examples. So let's consider this very simple function f of x equals x, and we know the graph is just a straight line through the origin with the slope 1, right? And as you can see, if I evaluate this function at 1, you get a 1. f1 equals 1. F at -1 is -1. So more generally, f at x is x. But if I change my input to opposite, I use -x as the input, then the output is -x, right? The output also becomes opposite. So if a function satisfies this property, so f at the opposite of x is negative, or say the opposite of f of x. Right? So you change the input to opposite, the output becomes opposite. Okay, clear? So if a function satisfies this property, we claim this function is an odd function. So algebraically speaking, f at -x, right? So it's f at the opposite of x, right? Is the opposite of f at x, right? So f at -x equals -f of x for any x in the domain. For any x in the domain. So if a function satisfies this relation, we say this function is an odd function. Graphically speaking, now you see, So suppose this x is an input to this function, then f of x is the output. If I change the input to the opposite of x, then you have a negative x here as the input. Then the output becomes also opposite, right? Negative fx. You see? So these 2 points, obviously, these 2 points are symmetric about the origin, right? About the origin. Okay, so for example, if this is 1, 1, let me say, if this is 1, 2, then this will be, if you use -1, you get a -2 as the output. Okay, you change the input to opposite, the output becomes the opposite, right? So this graph, obviously, you have a point here, 1, 2, then you have a corresponding point, -1, -2, and vice versa. You have a -1, -2 as a point on the graph, then you have a +1, +2 as the point on the graph, right? So you have the symmetry now. Okay, it's called the graph is called symmetric about the origin, right? About the origin. Okay. Now let's consider this example here. F of x equals the absolute of x, and we can write this function in a piecewise manner, right? Remember, if x is greater than or equal to 0, absolute of x is just the x itself, because now x is non-negative. If x is less than or equal to 0, then the absolute of x becomes its opposite, right? So it's negative x. Now, can you sketch the graph of this function? I think you learned this in algebra 2, right? This is called the absolute value function. So, you know, when x is non-negative, the graph should be the graph of this line, y equals x, right? This line, positive slope, slope 1. But if x is negative, then the function f of x is negative x, so it's aligned with the -1 as the slope, right? So you get this V shape, right? V shape. And obviously, so this V shape is symmetric about the y-axis. Algebraic speaking, so for, suppose you see you use 1 as an input, you get 1 as an output. But if you use the opposite of 1 as the input, you use the -1 as the input, then the absolute of the -1 is still +1. So meaning what? You change the input to opposite, the output does not change. Same, right? So 1 as the input, -1 as the input, they have the same output. Okay, that's why the graph is symmetric about the y-axis. So you have a point at the right, you have a corresponding point at the left. These 2 points have opposite x coordinates, but the same y coordinates, right, at the same level. So of course you have that at the left and right symmetry. Clear? So if a function satisfies this property, we say this function is an even function. So algebraic speaking, f at a negative x and f at a positive x are the same now for any x in the domain. So then the graph of this function should be symmetric about the y-axis. Is that clear? Now let's consider this function here. F of x equals x squared plus x. Is this function even or odd? So we can do that test now. Okay, I'm going to do this problem on a separate page. Okay, so you know how to test if a function is even or odd or neither. Okay, neither even nor odd. So consider this guy. So we know if the function is even, we require what? F at the negative x and f at x, right? Opposite inputs lead to same what? Outputs, right? So if function is even, f at negative x is the same as f at x. If the function is odd, then f at the opposite of x and f at x should be what? Should be opposite. Remember that? Right? So f at negative x is negative of x. So basically, in order to test even or odd of a function, for a function, you just need to check this. So here, so let's see, my f of x is x squared plus x. If I change the input to the opposite, what do you get? Remember, x is simply a placeholder, right? A placeholder. So when you have x as the input, you get x squared plus x. If I use negative x as the input, then you should have what? This negative x squared plus this negative x, right? Got it? So basically just replace x by negative x. So f of negative x is negative x squared plus negative x. X is a placeholder. You can replace x by negative x. You can replace x by an expression, by a number, okay? So if you simplify this, negative x then squared, you get a what? Positive x squared, right? And plus minus negative x is minus x. So f at negative x is x squared minus x. Is this the same as f of x? What is f of x? F has x squared plus x. Here is x squared minus x. They are different, right? This is not the same as f of x, because f of x is x squared plus x. But is this the same as a negative of f of x? What is negative f of x? You just multiply this whole thing by negative 1, right? So it's negative x squared minus x. Is this guy same as negative x squared minus x? Again, not, right? So f at a negative x is not a f of x. F at a negative x is not a negative f of x either. So what you can say? Then f of x. So when you have this, you know this function is not even, right? When you have this inequality, you know this function is not odd either. So this function is not even, not odd. Okay. So the graph, you don't have the symmetry of this graph. Okay. So this function is neither, or say neither even nor odd. Clear? Okay. And if you want, you can draw the graph of this function, x squared plus x, and the graph of this function looks like this. This is a parabola, right? You learn in algebra 2. The parabola x squared plus x, and it has two zeros, one at 0, one at a negative 1, right? Do you agree? So it looks like this. This is y equals x squared plus x. So it is equal to 0 at 0, which is equal to 0 at negative 1. Okay, with this axis of symmetry here. Obviously, this curve is not symmetric about y, right? It's not symmetric about the origin either, right? So that's why it's not an odd function, it's not an even function. Okay, now you try. This is the third problem today. If f of x is an order function, I tell you f of x is an order function, okay? And 5, negative 3 is a point on its graph. Then which point must also on its graph? 30 seconds. This should be quite straightforward if you understand the definition of an order function, okay? For an order function, if you change the input to opposite, then output also becomes opposite, right? For an even function, if you change the input to the opposite, the output does not change. Okay, f at 1 and f at negative 1, same. F at 2, f negative 2, same, even. Okay, for odd, then it's opposite. Opposite input, opposite output. So f at negative x is a negative f of x. Okay. So which point must be on the graph? Obviously, answer what? Answer C, right? Answer C. Okay. So answer C. So as you can see, if you draw the, so I'm not going to draw these points here. These points. So this is y coordinate. So this point here is on the graph, 5, negative 3. Suppose this is a 5 here, negative 3 here. Okay, so this is a point here, right? 5, x equals 5, y equals negative 3. Then if you change, so that means you will use 5 as the input, you get a -3 as the output. But this function is odd. So if I change the input to opposite, I use -5 as the input. Then I should get the opposite negative of -3, which is the +3 as the output now. Right? So this point here should be what? -5, +3. So these 2 points are symmetric about the origin, right? About the origin, right? If you connect here, if you connect these 2 points, right? They fall on the line with equal distance from the origin, right? Like that. Symmetric. Got it? So the answer should be C. Okay, should be C. I think this should be straightforward. Okay. Now, next. So far we just covered some essential concepts about the functions and the essential properties about the functions. Okay. So I know you learned this stuff right probably in algebra 2, but it's very important you understand them very clearly. Okay, fundamental things. Now, next we are going to consider okay. Okay, so next we are going to consider transformations of functions. Transformations of functions. Have you guys watched the movie Transformer? No. Transformer, a series of movies, Transformers. Okay. So when we say transformations of a function, algebraically, we do operations on f, right? Say we add a number to f of x, we change x to x plus 2, right? Something like that. We multiply x by 2. We do these algebraic operations on f. That's called transformations on f. Graphically speaking, when we do transformations on function, we move, or say we shift the graph of this function f, or we deform that graph. Okay, so we do deformation or shift to the graph of a function. Then we say we do transformations on the function. So let's consider the following transformations. So I think most transformations have been studied in algebra 2, but I will emphasize a little more about horizontal compression. Okay, I think that's a confusing part. Okay, when we do transformations. So let's do some simple ones first. Suppose we have y equals f of x. Right? The graph is this green curve here. Now I can make a new function by transforming this f of x. How to transform this f of x? I just add f of x by c. I get a new function. So my new function is y equals f of x plus c. Basically, I have a machine. I call it f machine. X in, f of x out. Now I can make a new machine. X in, the output of f of x is added by c now, right? For each output is added by c. So f of x plus c. So graphically speaking, as you can see, suppose x naught is the input for f, then output is f at x naught. But what's the output of this y equals f of x plus c? You just add f x naught by c. So that point, x naught, f x naught, this point is shifted in a vertical direction, right? Because you add a c. If c is positive, you lift that point upward by c units. Do you agree? If c is negative, so if you subtract the f x by c, suppose c is positive, then you just move that point down by c units. This is true for any points on the graph of f of x, right? So basically, the graph of f x plus c can be obtained by shifting the graph of f of x either upward by c units or downward by c units. Do you agree? Depending on you add c or subtract c. That's something I think you know. It's called a vertical shift. Okay. So for example, I think you can see, suppose I have y equals x. My f of x equals x. Now I consider y equals f of x plus 1. You have x plus 1. As you can see, basically you just shift this line upward by 1 unit. Right? You get this blue line. If you consider y equals x minus 1, then you get this line below. Right? You shift, it doesn't push this green curve downward by 1 unit, right? That's it. Very simple. Right? I think you saw this example. Y equals x squared. This is a green parabola, right? Through the origin. Now, if I consider y equals x squared plus 1, so f of x equals x squared. What is f of x plus 1? It's just x squared plus 1. Then you just add all the output by 1, right? So this basically you shift the graph of y equals x squared, this green parabola upward by 1 unit. Okay, upward by unit. And similarly, y equals x squared minus 1 is obtained by shifting y equals x squared downward by 1 unit. Okay. So next, horizontal shift. Okay, so suppose this green curve is the graph of y equals f of x. X not in, fx not out, right? We have this point here on the graph of y equals f of x. Now I'm going to construct a new function by replacing x with x minus c. So I have y equals f of x minus c. So what's the graph of this function? The graph of y equals f of x minus c, if c is positive, can be obtained by shifting this green curve y equals f of x to the right by c units. Do you know why that's the case? To understand the reason here, right? Suppose this is my f of x. Okay, f of x. Now suppose I have a point. This point here, suppose is 1 and 2. Suppose this is the point on f of x. Now I have a new function. Suppose I call it f of x minus 1. So for f of x minus 1, we know f at 1 is equal to 2, right? So for f of x minus 1, if you supply 2 as the input, so use 2 as the input. So then you know, suppose I use, so here f at 1 is equal to 2. So you get this point here. But for this f of x minus 1, if my x value is 1 plus 1, I add this y coordinate. So here this y coordinate is 1. I add this coordinate by 1 unit. 1 plus 1, right? This distance here is 1. Then you use 1 plus 1 as the input for x, right? So then it's f of 1 plus 1 minus 1, which is equal to what? f1, which is equal to 2. So at this location here, at 1 plus 1, you get the same output. You see that? Right? Same output. So any point on f of x, you can find the corresponding point 1 unit to right. So that means the graph of this function is basically just the horizontal shift. Okay, horizontal shift of this graph. Okay, horizontal shift of this graph. You get that? Right? So in other words, so I have this function y of f of x minus c. If I use x not plus c as the input, then what is the value of this function? So you replace x by x not plus c, right? We have f of x not plus c minus c. Then you get fx not. See? So on the green curve, the coordinates are x naught, fx naught. But if you want to get this same fx naught as the output on the red curve, you need to use x naught plus c as the input, because this new function is f of x minus c. In order to get that same output, now I need to use x naught plus c as the input. It needs to increase your x naught by c. Then you subtract c, you get the same x naught. For f, you get the same output, right? So that's why any point here, you have a corresponding point there. Okay, separated horizontally by c units if c is positive. Okay, so you remember this fact. So graph of f of x minus c, if c is positive, can be obtained by shifting graph of y equals f of x to the right by c unit. If you have f of x plus c, c is positive, say for example f of x plus 1, then you shift the graph of y equals f of x to the left by 1 unit, right? In the same with the same reason, same argument. Okay, because now in order to get f of x naught as the output, for f of x, I use x naught. for x plus c, I need to use x naught minus c now, because the x naught minus c, then add c is x naught, fx naught, right? So let's see. So you need to use a point to the left of x naught, okay, to get this same level here, okay? So the graph of f of x plus c is obtained by shifting the graph of f of x to the left by c unit, okay? If you add c to x, and c is positive. So let me do a few examples. So this time I'm going to do this example in decimals. Okay, so you can see that very clearly. Okay, let me use decimals to demonstrate horizontal shifts. Okay, so I'm going to draw the graph of y equals x squared. This parabola right here. Okay. Right? This parabola. Now, this is the f of x. Okay, f of x equals x squared. Now I replace x by x minus 1. F of x minus 1. So then y, what is it? If f of x equals x squared, what is f of x minus 1? Then is the square of what? X minus 1, right? Right? So this is f of x minus 1. That replace x by x minus 1, right? The top guy is f of x. The bottom guy is f at x minus 1. So it's x minus 1 squared. What do you see? The blue curve is f of x minus 1. See, obviously, you just shift this red curve to the right by how many units? By 1 unit, right? So what's the vortex of x squared? X equals 0, y equals 0, right? Now for this function here, in order to get a 0 at the output, now you need to use 1 at the input now, right? 1 minus 1 and square get 0. See, the vortex now is 1, 0. See, now the vortex is shifted, right? See, from 0, 0 to 1, 0, 0, 1, 0, right? And this happens for all the points. Yeah? So it's shifted to the right by 1 unit. Now, how about the graph of if I change this function to y equals x plus 1 squared. Let me undo this one. You get this green curve now. See, the green curve is obtained from that red curve by shifting that red curve to the left by 1 unit, right? See, the origin, the vortex for the red curve is 0, 0. But for this curve now it's negative 1, 0 now, because you use negative 1 as x to get a y 0 y value, right? For the left. Got it? So now you try this problem here. Okay, I give you the graph of y equals f of x, this green curve. Okay, and y equals g of x. I tell you y equals g of x. The graph is obtained. The graph of y equals g of x is obtained by shifting the graph of f of x both vertically and horizontally. Okay, as you can see, the starting point, the left end point of this green curve is 0, 1, but here is negative 3, 2. Can you tell me what is g of x in terms of f? Okay, think about it. So how you should shift this f of x to get that g of x? This is the fourth question today. Fourth poll question today. Oh, fourth quiz question today. Okay, so which answer choice is for g of x? What did you get? Anyone? A. Most of you guys chose A. Is A correct? So as you can see, I know this G of X is obtained by shifting this F of X, right? How to shift that F of X? You can just check this starting point here. So this point here, the coordinates are 0, 1, right? So now you see this point is shift to which point? To this guy, right? To -3, 2. So obviously you need to do this shift here, right? You need to shift upward by how many units? From 1 to 2. You shift upward by 1, right? Then you shift to the left by how many units? From 0 to -3 by 3 units. Or you can do the other order. You can shift to the right by 3 units, then upward by 1 unit. Doesn't matter in this case. The order does not matter in this case. Okay, when you do shifts. So when you if you shift this curve upward by 1 unit, let me draw this curve here, the middle curve here. Then you get this curve. Right, like that, right? You shift this green curve upward. So what's this function here? This guy. Y equals f of x plus 1, right? Just add 1, right? To f of x, you get that orange curve. My drawing is a little awkward here. Let me make this a little bit better. This is better. Okay, shift upward, right? Then you shift this guy to this direction by 3 units, right? To the right, right? See, any problem is shift to the right, right? You start from this curve, and you notice g over x is simply what? Y equals you just replace this x by what? By x plus 3. So it's f of x plus 3 plus 1. So the answer is A. A is indeed correct. Okay, right? You add 3 to x, you shift to left by 3 units. Then you add 1, you move it up by 1 unit. Okay. Now, let's consider reflections. So y equals f of x. This is a machine. Now I make another machine. So basically, the output of this machine is just the opposite of my f of x, right? So this is y equals f of x. This is y equals negative f of x. So how about the relations between their graphs? So now you see, I use x naught as the input. I get f of x naught as the output from f. But I get a negative f of x naught from negative f, right? Because you need to multiply the y value by -1, right? It becomes the opposite. So any point on above x-axis, you have a corresponding point below x-axis. So what do you see? You see the symmetry about what? About the x-axis now, right? So when you multiply, you see the graph of negative f of x is simply the reflection of y equals f of x about this x-axis, right? If you put a mirror here, then the image of this f of x is this negative f of x, right? When you see in the mirror, clear? So that's called the reflection of a graph in, or say, about the x-axis, okay? And similarly, if I change x to negative x, what happens? So for f of x, I use x naught, I get f of x naught at the output. For f of negative x, if I want to get f of x naught at the output, I need to use what? You need to use negative x naught, right? Negative x naught is x naught. Clear? So, for example, on the green curve, suppose I have this point here is 1, 2. On this red curve, now in order to get a 2 as the output, I need to use -1 because it's negative of -1. It's negative x, right? Negative 1, which is 1. F1, right? Which is 2. So now you see, whenever you have a point to the right, you have a corresponding point to the left. So you have this left-right symmetry now. So if you change x to negative x, so we see the graph of f of negative x is a reflection of this f of x in y-axis. Okay? So remember these two reflections, okay? F to negative f, reflection about what? About x. X replaced by negative x reflection about what? About y. Got it? About y. Now, vertical stretching or compression. I think you know this one, right? Suppose this green curve is y equals f of x. Now, suppose I multiply f by c, I get a new function y equals c f of x. All right, I do the transformation, right? So if c is bigger than 1, then you see for same input. So here is f of x naught, but now is c times f of x naught, right? So you scale, you multiply all the y output by c now, right? So if c is bigger 1, you make that curve further away from what? You make that curve further away from the x-axis, right? Of course, at 0, right? If you have a line here, 0 multiplied by c is still 0, right? So this is called as vertical stretching. You stretch that y equals f of x, this curve, away from what? From the x-axis in the vertical direction. Okay, so it's a vertical stretching when c is bigger than 1. And similarly, if c is positive but is less than 1, between 0 and 1, then you multiply that f of x by c, you make your y coordinate closer to what? To the x-axis. So this is called a vertical compression now. Got it? To summarize, if c, so when you consider the graph of y equals c f of x, if c is bigger than 1, graph of f is stretched vertically by a factor of c. If c is between 0 and 1, forget to put it as greater than 0, okay? So if c is between 0 and 1, then graph of f is compressed by a factor of c. Got it? Okay, I think we saw this in algebra 2 too, right? So hopefully this is clear to you. And this one is kind of harder to comprehend sometimes. So what happens if I change x, I replace x with cx? Suppose this green curve is y equals f of x. Okay, I want you to listen carefully. Okay, this green curve, y equals f of x. Now I make a new function by transforming this f of x. A new function is y equals f of cx. So that x now is replaced by cx. What happens if c is bigger than 1? So look at these 2 points here. Suppose I supply x naught as the input to f of x. Then I get f of x naught as the output. In order to get f of x naught as the output from f of cx, what x value I should use now? I need to have, we know f of x naught, right? So this cx should be x naught now, right? So if cx equals x naught, that means x is x naught divided by c. So if c is bigger than 1, that means suppose x naught is here, then x naught over c over something bigger than 1, you're getting closer to y-axis. That's why it's called a horizontal compression. So when in this case, when c is bigger than 1, so you have a curve here, you replace x by cx, then the curve, you compress that curve toward the y-axis. Because I can use a smaller x value to achieve the same output. For f of x, for example, for f of, suppose that f2 equals 1. For f2 equals 1. Now, if I have f of 2x, I just use the x equals 1 to get a 1 now, right? Do you agree? So think this way. Suppose I have f of x, right? Suppose for this function, I supply the 2 as the input, I get a 1 as the output. Now I have a new function, which is called f of 2x. So how to get the 1 as the output? Now I just need to use x equals 1, right? So for this function, when x equals 1, I have f of 2 times 1, which is f2, which is equal to 1. Right? So I get the same output, same level, f of x, 1 as the output. For this f of x, I use 2 as the input. But for f of 2x, I just need 1 as the input now. Right? So I use an input closer to y-axis. That's why so for the curve, so it looks like this curve is getting compressed toward the y-axis. So it's called a horizontal compression. Okay, if c is bigger than 1. And similarly, if c is less than 1, bigger than 0, then it's a horizontal stretching now, right? So x naught, fx naught. But for f of cx, now I need to use x naught over c. But because c is less than 1, for example, c is 0.5, x naught over 0.5, now is 2x naught, right? You need to use double x naught to get the same output at the same level. So you have a pointer here, then you have a corresponding pointer on that curve. which with a bigger x coordinate to get the same y coordinate. So that's called a horizontal stretching. Okay, to summarize, you need to remember this. Okay, when you consider y equals f of cx, y equals cx, if c is bigger than 1, compression or stretching. Now it's compression now toward the x y-axis. If c is less than 1 but positive, then it's a stretching away from the y-axis. Okay. If this is kind of confusing to you, let me again use decimals to give you some examples. Okay, suppose I have y equals x squared. I use x squared as example. Okay, this is my f of x. What is f of 2x? That is a square of what? Of 2x, right? F of 2x. This is the f. Okay, f of x equals x squared. What is f of 2x? F of 2x is the square of what? X. What do you see? Compression or stretching? Compression, right? So the x squared is this purple curve, right? Purple, right? But when you have 2x squared, you get a 4x squared. Basically, it looks like you compress. It's a purple curve toward the y-axis. Got it? Now, what happens if I change that x to half of x? Let's see, now is half. So f of x is x squared. What is f of half of x? Then y is equal to f of half of x. You replace x by half of x, right? So the x over 2. Then squared. See? Horizontal what? Stretching, right? So if c is less than 1, now it's stretched away from the y-axis. Do you see that? Right? Stretched away from that. Okay, so hopefully don't get confused with the vertical. When you have vertical situation, c bigger than 1 is stretching. C less than 1 compression. But for horizontal, c bigger than 1 is a compression. C bigger less than 1 is a stretching. Okay, opposite. Okay, opposite. So so you guys try this problem here. Okay, this is an interesting problem. Y equals f of x. The graph is this green curve. Okay, and y equals g over x is obtained from the graph of y equals f of x by refraction and compression. Refraction and compression. So which one can be g of x? Can you figure that out? So first of all, you need to do a reflection, right? To reflect about which axis? About an x-axis, right? Obviously, right? You get the black guy. After you get the black guy, then you need to do a compression. So what kind of a compression you need to do? You need to do the both vertical and horizontal. Why? Can you see that? Because this red shape actually is shorter, right? In the y direction is shorter than the black guy. And in the x direction is narrower, right? It's narrower than the black guy. Okay. So what you can say now? Think about it, okay? Which one is the correct form for g of x? Have you guys figured out? First of all, you reflect f of x to this black curve. So what's the form of this black curve? Y equals what? negative f of x, right? You just multiply all the y value by negative, right? Make it flip it down, okay? Then you compare this red curve and this red curve, black and red curves, okay? So what do you see? So first of all, you notice the range of y for the black guy is bigger than the range for the red guy, right? So that means there must be a vertical stretching or compression, right? You compress that red guy toward the x-axis. Okay, so let's do that compression here. Okay, so it multiply by, obviously, according to this formula, cannot be 2 now, right? Must be something less than 1. So it's a negative fx multiplied by something less than 1, bigger than 0. So obviously, it should be half. Okay, so if you do that, then you get this curve here. Right, something like that, right? See, so this orange curve can be regarded as y equals half times negative f of x. Okay, then the red curve now, okay, the red curve and this purple curve is they are about the same y level here, okay, about the same level. But the red curve is narrower than the orange curve, right? So that means you also need to apply a horizontal compression. So you replace x by something cx, right? Well, c should be bigger than 1. So obviously, the answer choice should be B now, right? So this c is bigger than 1. So it's a horizontal compression. So the final answer should be B. Okay, let me see how many of you got it. Okay. Give me some time. Okay, I want to finish one more thing. Okay, please hold on. So in the second portion of today's lecture, we consider the transformations of f. Okay, so hopefully you are comfortable with all these transformations. Okay, so later on in your homework, you do practice. Lastly, we want to consider combinations of functions. And you can add 2 functions, you can subtract 2 functions, divide 2 functions, multiply 2 functions. Those combinations are very simple. Okay. So what I want to emphasize here is composition of functions. Okay. So let me finish this part here. So keep in mind, a function is a number machine that takes a number as an input and spits out a number as an output, right? So suppose I have this machine G here. And G takes input X and spits out the output G of X. Because this output G of X is a number, so then this G of X, this number can be the input to another function. Do you agree? So you can supply this output from G as the input of another function, say F. So now you have a chain of functions like this, connected. Right? Basically, it's just you have 2 machines and connect them. Then you use 1 machine to produce this, then use the product of this machine and as the input for another machine. Clear? Right? For example, in your home kitchen, you have a fruit washing machine. Right? You put the fruit in that machine. The machine washes the fruit. Then you get a clean fruit. Then clean fruit is supplied to the juice machine. Then you make a juice. Right? Like that. Okay. So if you do this kind of connection, we get the so-called composite functions. So consider this a concrete example here, right? So in this diagram here, we supply X to G, and G spits out G of X as an output. Then this G of X as an output, also as a number, is supplied to F. Then you get F works on that G of X. You get F of G of X, right? So this form here is called a composite function, F of G of X. Got it? So for example, suppose G of X is X squared. F of X is the square root of X plus 21. So if I ask you, what is the F of G of 2? So now you supply 2 to G. What do you get? G of 2 is 2 squared, right? You get a 4. Then this G of 2 as a whole number is supplied to F. So F of G of 2. It should be 2. I think I made a mistake here. Right? Yeah. So f of g over 2, then we know g over 2 is 4, so it's f of 4. And we know f of x is square root of x plus 21, so it's square root of 4 plus 21, you get a 5. Okay, you can fix your notes. Okay, I made a mistake here. Okay, typos here. Now, if I switch the order, suppose I supply x to f, then use the output of f as the input of g. So I switch the order of these two machines in this chain here. You get different products, as you can see, right? So g of x is x squared. So what is g over f of x? So then you treat f of x this as a whole, or as a number. So g on x is x squared. G on this f of x would be f of x squared. Now, what is f of x? Or f of x is square root of x plus 21. So it's square of square root of x square of square root of x plus 21. You get this form here. But if you do f of g over x, then you say, oh, f of x is the square root of x plus 21. So what is the f of g? You replace x by g now, right? So it's f of g should be square root of g plus 21. But what is the g? G is x squared. You get a x square root of x squared plus 21, which is different. So normally f of g over x is different from g over f of x. Okay? So if you change the order of these two functions, you get different composite functions. Keep that in mind. Okay? So this is the formal definition. Okay? So the composition of the function f with the function of g is f of g of x. Okay, this g of x is called an inner function, right? It's inside of g. And f is called the outer function. Okay, so you supply x to g first and make output put g of x. Then that the output g of x is supplied to f. Okay, so another way to write down is f composition of g. I put x. This is another notation, but I don't like this notation that much for elementary courses, okay, but in advanced courses, this is very important. This notation is very important. And if I want to find the domain of this f composition of g, then you need to make sure what? You need to supply x to g such that g is happy. Okay, g can take that x. Then g makes the output g of x. That output make f happy, right? F can take that g of x as the input. Okay, so you need to check both. Check both. I want to show you one example, then we stop here, okay? Okay, so please hold on. So for example, let's consider this problem here. F is x squared minus 16, g is square root of x. What I want you to find the domain, find the composition for f and g, and also its domain. So first of all, you tell me, what is the composition of f and g? According to the definition, is f of g of x, right? And keep in mind, f of x is x squared minus 16, right? X is the placeholder, right? You supply the x for the f, you get x squared minus 16. Now I'm supplying g of x, treat g of x as a number, okay? Because it's the output of g, right? Treat g as a number. So this g is supplied to f. Then what's the output? According to the mechanism of f, should be g squared minus 16. Do you agree? So this would be g of x as a whole get squared minus 16. But what is that g of x? What's that output? So you supply x to g, you get the output. We know g of x is square root of x, right? Then you plug in square root of x for g. It's square of square root of x minus 16. If you simplify, you get x minus 16. Now let me challenge you. What's the domain of f of g of x? What's the domain of this function?
All real numbers.
All real numbers? Okay, that's a very common mistake. Okay, so be careful. Okay, that's what I want to show you. You cannot just use this final form here to say all the domain is all real numbers. Keep in mind. So x must make g happy first. So let me tell you, what's the domain of F? What's the domain of F? You can tell that, right? Don't be afraid. What's the domain of F? X can be or real numbers. This is okay, right? For F, all real numbers, right? Because X squared minus 16. But what's the domain of G? What's the domain of G? Yeah, or non-negative real numbers, right? X should be what? Greater or equal to 0, or non-negative numbers. Clear? Now, let me ask you, what's the domain of F of G of X? When you supply X, G must be happy first. Then G is happy, produce a product, then the product is supplied to F, make F happy. So what's the domain? Yeah, non-negative numbers. Okay, not all the real numbers. Because if you look at the final form here, X minus 16, you say, oh, all real numbers. But keep in mind, this X minus 16 comes from F of G. So you know, so the domain of F of G, keep in mind that this F is okay. F can accept any G, right? Because all real numbers. You just need to make sure G is happy. So the domain of F of G of X should be all non-negative numbers. Okay, that's the domain. As long as G is happy, F should be happy because F can take any real number as an input. Okay, so that's something you should be very careful. Got it? Do I have more questions for you guys? Okay, just a quick practice. Okay, last one. Okay, then we're done. Okay, sorry for the delay. This is a very simple one. F is X squared minus 16. G is the square root of X. What is the F composition of G at 16? What's your? So what do you get? So you supply. So this means is F of G of 16, right? So when you supply 16 to G, so G of 16 is equal to 4. Then you compute F at G is F at 4, which is the 4 square minus 16, you get a 0, right? So the answer should be C. Okay, so that's all for today's class. So you guys are tired. Okay. See you guys next time. Okay. Do your homework.